the shape of a quantitative distribution. Now, tomorrow we'll talk about just describe a quantitative distribution. And when I ask you to describe a quantitative distribution, there are 5 points for criteria, okay? So when I'm trying to describe a quantitative distribution, I need to make sure, first and foremost, I include context. This is your first criteria point, context. Does your answer include context? And of course, when we say context, we're referring to the who and the what. Do you talk about who this data is about? And do you talk about the variable? We know, and most of the times, we just don't want you to be very robotic. And if you just say like the distribution, well, what distribution? What is the distribution referring to? That's what we mean right there. So first and foremost, context is included. In tonight's homework, when I ask you for these problems, I'm asking you for context as well. And then we have an acronym for the remainder ones, and it's called SOCS. S-O-C-S. This is the second, third, fourth, and fifth. And today we're just going to be focusing on the first S of SOCS. And as you've read, the first S is standing for shape. What does the O stand for? For anybody who did a little bit extra reading in terms of the reading guide, I might have went ahead or did some of the reading. What does the O refer to about a quantitative distribution? I know it doesn't say, nowhere in your reading did it say SOCS, but it referred to something that you need to talk about. What is another property of a quantitative distribution that we need to describe?
I think it was outliers.
Perfect. Outliers. What does the C stand for?
Center.
Center. And what does the other S stand for?
Spread.
Very good. Now in today's class, we're just focusing on here for today. We're just focusing on shape. Tomorrow, we will be talking about outliers, center, and spread. So how do you talk about those? How do you do them from a graph? How do you do them from the summary statistics? We'll focus on that tomorrow. Okay. I also usually like put a star next to the outlier part, because outliers are there. If there's not always an outlier. So if there's not an outlier, you don't mention it, it's perfectly fine. So let's talk about shape. There are 3 basic shapes that we refer to and talk about in statistics. Okay? Quantitative distributions. So when talking about shape, we're talking about graphical representations, or we have been given, or we will be drawing graphical representations for quantitative distributions. Now, later on in this week, Thursday and Friday, we will start covering some of them, and next week we'll cover the last one. So we're going to spend multiple days going over the graphical representations. Today, I am not asking you to make any graphical representation. They will be provided for you. So there are histograms. There's a histogram that we can draw. There's a dot plot, a stem plot, and a box plot. For our course, these are the four that we're gonna be using, and each of these four can be used to describe shape. Okay. There's limitations for the box plot, though. There are some limitations for the box plot, but when we cover box plot, we'll talk about that. So in tonight's homework, you're going to be given histograms, and all the problems that you're going to see tonight are you're going to be asked. You're not going to be asked about any of them. You might just get a description, and there's certain things that we need to know about properties of distributions. The beginning of your homework problems, you're going to look at it and say, wait a minute, there's no graphs, there's no nothing. How do I describe the shape? Well, the idea is that you should have an idea of what the populations look like. And so there are, first off, let's go with the very first one, which is called uniform. Uniform distributions. A uniform distribution is, so all of these, sorry, when we talk about these, we were talking about the responses. All right, we're talking about the responses. So in this case, the responses are outcomes. The outcomes are all equally likely to occur, are close to it. So if you think about all the different outcomes that could occur, a uniform distribution basically says that the chance of, every single outcome basically has the same chance to occur. An example would be the outcomes of rolling a single die. So if we're rolling a die, what are the different outcomes in rolling a die? If we roll a die, what are the different outcomes?
6.
Yeah, but what are they?
Dots.
No, but what are they? There are 6 outcomes. What are the 6 outcomes?
Numbers.
Yeah, so what are they?
1, 2, 3, 4, 5, 6.
So the outcomes of rolling a die are 1, 2, 3, 4, 5, 6. Yes, they're numbers, and yes, there are 6 of them. The outcomes specifically are 1, 2, 3, 4, 5, 6. Now, each of these outcomes, when you roll a die, are equally likely. You have a same chance to roll a 1 as you have a rolling a 2, as rolling a 3, as rolling a 4. So if I were to look 1, 2, 3, 4, 5, and 6, basically, and they might not be exact. Oops, it's a little too wide there. That's still a little. And you'll have some frequency. We'll learn how to draw histograms and stuff like that. This is not a bar graph, but if you look at this graph, well, representation, it's very boxy, right? When we get outcomes that are very boxy, we refer to this as uniform. And I know this outcome of the 5 is a little bit lower the way I've drawn it. I mean, it'll probably be a little bit closer to the top values. Each outcome, is the same. You have an equal chance. There's an equal number. If you were to do, for example, if you were to roll a die 6,000 times, then you would probably expect about 1,000 ones, 1,000 twos, 1,000 threes, 1,000 fours, 1,000 fives, and 1,000 sixes. Now, You're not going to get exactly 1,000 of each, right? There's probability and there's chance, but you're going to get overall relatively close. We refer to this as a uniform distribution. Now, uniform distributions typically happen with probability outcomes. So games of chance typically is where you have uniform distributions. Okay. Second type of distribution, 2. Now, the next ones all come from actually a subset. So the next ones are called unimodal and blank. Okay, so I guess I'll put a 2, and we'll call them 2A, 2B, and 2C. There is a 2A, a 2B, or a 2C. In other words, if you say unimodal, technically we should always be talking about things that are unimodal and something else. Now, when referred to modal, that means that the distribution has outcomes more likely around a central location. Okay, so unimodal, and you can think like the word mode comes from unimodal. Now, this is the only time where we kind of say the mode. When we refer to the mode, I usually count it as the mounding part, because I don't like to talk about mode the way normal students talked about mode. The outcome that happens most often. Sometimes the outcome that happens most often technically isn't a mode, so we got to be careful about that, because it could be like an outlier type of thing. But unimodal typically happens when you have now there are 3 types of unimodals. There are 3 types. There is unimodal and symmetric. There is unimodal and skewed left. And then there is unimodal and skewed right. Some students and some of you are probably going to do it, and that's okay. We're going to learn from it if you do. Some of you might say things like, "Oh, it's symmetric and skewed left." Okay, whoa. Those mean 2 different things. You're contradicting yourself. So we got to be careful about those type of things. You can only be symmetric or skewed. And if you're skewed, which direction are you skewed? Are you skewed left? Or are you skewed right? We'll take a moment to talk about what those mean. Some people are going to just say unimodal. And I can't give you credit for the shape, because in order to give you the shape, I need to say unimodal, and I need to be a little bit more specific if the information is provided. Now, sometimes the information isn't provided, like in a box plot. That's where that's going to happen. And so in a box plot, sometimes saying unimodal is the answer, and that's because that's all you can talk about. But right now, there's not going to be any problems that are going to happen like that. You would tell me unimodal and skewed left, unimodal and symmetrical. So let's now go through each of these. Okay? 2A. Let's talk about unimodal and symmetric. This is our most important one out of all of them, okay? This is the one that happens most often, and we're going to do a lot of statistics on unimodal and symmetric. Unimodal and symmetric usually occurs naturally with a central average population. So, for example, we can talk about, like, we can't spell, weights of males. We're talking about weights of males. Most males, now there are males who weigh very little. There are males who weigh quite a bit. Okay, same thing with females, but I'm focusing on males only. So when we talk about the distribution, you might have we'll talk about 12th grade males. There might be a male that weighs, like 100 pounds, and there may be a male who weighs 300 pounds. Okay? But, let's actually, for the purposes of this, let's go with 200. But, I mean, and it's not, and this is not scientific in terms of these values right here, but most males will say are somewhere around 150 pounds. All right? So when I think about how this distribution looks, the distribution might look something like this. Now notice that there is one mode, or if we kind of like go and follow the graph, it goes up and then it goes down, and that mound is right in the center. Now, this is not to say all the males weigh 150 pounds, but most males are more likely to weigh closer to 150 pounds than they are to 100 pounds or 200 pounds. Now, you might have another male that's out over here that talks about it's like 300 or something like that. We'll talk about tomorrow as that being an outlier. You're not focusing on that. Outliers, if there are outliers, we really don't talk about them in regards to affecting the shape, because one person shouldn't change your perception of the entire population. One person, one thing, maybe even two, shouldn't just talk about it. But our shape, we just care about the majority part. So notice the central. Now there's a lot of different things. Weights, we can talk about heights. We can talk about, there's lots of different ones. But if you think about it, if you think and say, well, there's some that are going to be small, but not many. There's some that are going to be high, but not many. And most of them are going to be somewhere in between. In those cases, we have something that is skewed. That's something that's symmetrical. 2B. Unimodal and skewed left. This typically occurs when there is a low ceiling but stretches further for low values. So an example here would be high school graduation rates. If we were to look in BPS, if we were to look in Boston Public Schools, most of them you would say is around what? What are most high school graduation rates around? Anybody have any ideas?
70.
Oh, it's a little higher than that. It's high 80s. High 80s, I would say. So 80s, maybe even 90s. All right. Most of them are actually closer. Typically, a typical high school is around, and let's say some around 90%. Typical high school. That doesn't mean you're like, oh, I know some high schools that have very low. Well, that's the idea, right? There are lows. There are going to be low ones. Now, what's the max? What is the max? What is the max possibility for a high school graduation rate?
100%.
100%. You can't go any bit higher than 100%. Right? I don't know if any of them have it. So when we think about the graph, okay, here's 100%, here's 90%. The majority are around 90%, right? So the majority are where we're saying are about 90%. But, you know, the most you can get to is 100%. You can't go any further than that. So you stop at 100%. You can't go beyond that. So, but our mound, if I exaggerate it, let me exaggerate this a little bit more. Our mound is right around 90%. But wait a minute. As Mariana just said, there's schools that are like 80%, right? There's schools that are even lower than 80%. There's a lot of schools that are in trouble because their graduation rates are, you know, let's say there's 80, 70, 60. There are schools that have 80, maybe not as many. There are schools that have less than 80. There are some schools that have less, that have around 70. There are a little bit of schools that have around 60%. There may be even some schools that have 50% or are lower. So the responses are typically, when you talk about skewed, typically the typical, or what you think of as typical, is very, for skewed left, means that it's very close to the maximum. But the minimum might stretch out a lot further. So, you know, the minimum here, and it wouldn't be 0%. People have to graduate, or that just, we'll say the minimum is something like 50%. That's the lowest high school graduation rate in Boston. We'll say it's like 50%. If I give you this information, the typical is around 90, and you can't go further than 100, but the lowest is about 50. You can see from this that it skews to the left. It skews to low values. It is skewed left. There is a tail on the left. These are all things that words that we can say. Most people at the very beginning get these backwards. They'll think that this is skewed right because they'll see the majority, the typical, the high, the peak is on the right side. So they'll think it's skewed right. We always talk about the tail. We pulled it out, skewed left. 2C. Unimodal and skewed right. This typically, it's just the opposite. This typically occurs when the typical is close to the min, but max can be very high for many. Example. We'll talk about household incomes. Household incomes. Okay. What would you say is a typical household income? What would you say is a typical household income? I know. What is it?
1,500.
Whoa, a year, per year.
Oh, a year? Oh,
Yeah.
I thought you meant like how much they get paid a paycheck. But I don't know. 60,000.
60, 50, well, yeah, we go 60. We'll stay with 50,000, somewhere around there. 60,000, 40,000, 50,000, 60,000. So we'll go around $50,000. Okay, maybe closer to 60 if you have, you know, two people and so forth. Now I'm not asking for what would you consider a low? Now I'm not asking for minimum. I'm not asking for a minimum because of course the minimum is 0, and we can also think of it as 0. But what would you see? What you would say is low incomes? What would you think of as low incomes?
It's like a part-time, so like $7,000, 8.
Okay, we'll just keep the numbers nice and low, around $10,000, right? What would you consider high incomes?
150K.
Okay, so I heard 150,000. I would actually even go further. If I'm thinking about high incomes, I'm thinking like $1 million. And there's incomes, of course. Now, the minimum, of course, is 0. And the maximum is like $1 billion. We can think of it like that, right? There's people who make a lot of money. So you have this typical around 50, which is much closer to the minimum than it is to the maximum. It's much closer to what you would deem to be low than what you would deem to be high. And maybe you say $250,000 is high, but I think we still get the point across. So when I think about here, I have like 50,000, or I'm going to put it as K. I have 10K right here, 50K right here, 100K, and so forth. Most of mine are going to be right around 50,000, and it'll get a little bit smaller as we go to 110,000. It'll get a little bit smaller as we go, to like 150,000. But there's still households that make all the way out to the very, very far right. There's no maximum at all. There's really, in reality, there's no max to how much money you can make in a year, but there is a minimum. And so we say that this distribution is skewed to the right. That tail is being pulled to the right-hand side. That's skewed right. Finally, and to end our day, our third one is what we refer to as bimodal. Bimodals occur when there are two distinct populations that have two different typical outcomes. Now, where we talk about this, we're saying outcomes for the variable. It has to be for the variable, okay? Most people think, they'll think, oh, gender, male and female, male and female. There's a two. If I have both males and females, but it has to be for that question. So earlier on, for example, I talked about the weights of 12th graders. Let's just talk about, I said the weight of males. But now let me go to weights of 12th graders. All right? Now, do you agree that a typical female weighs less than a typical male?
Yes.
Yeah. Now, is that always true?
No.
No. And we're not trying to talk about always true. We're talking about a typical male being weighing more than a typical female. So, as such, it's like a blended. So, you might have, for example, we'll put this around 100, and this will be for the females. And if I did it for the males, we said around 150 for males. But if we were to combine this for 12th graders, and we were to combine both of these, then our distribution might look something like this. It's going to go up, it's going to come down, it's going to go back up, and come back down. So this is like the 100, and this is like the 150. And if you look at how the shape looks. It goes up, and then it comes back down, and it goes back up, and then it comes back down. And the reasoning behind this is because we have two populations of weights. The weights, this right here is maybe all you know. This is all you're given. The weights of 12th graders. And you're like, why am I getting binomial? Or why would it be bimodal? Well, the reason why it would be binomial is most likely because we have two populations. You have males who typically weigh more than females. And as such, we have really two populations. We have two distributions that are in the same population, or the same thing, the same distribution we're looking at. We could take apart these two distributions and look at just the males and just the females for them. Your homework comes from homework number, what number are we on? Is it 6 or 7?
7.
7 is from chapter 4. It's problems 5 and 6, and then 7 and 8. However, I only for 7 and A and 7 and 8A, I want you to just do shape. So the question says, like, describe the distribution. I just want you to describe shape. And then I still want you to, and then question 7B and 8B say, why do you think the shape looks that way? Oh, okay. So I want you to explain why that shape would be what the shape looks like on that one. But in 7A and 8A, it says describe the distribution. I just want you to do context and shape. It's 8/9/50. That's what I have for you today. I'll see you tomorrow. Or office hours.